All right, we want to do one more of these types of problems. Again, we have a situation that it's not apparent that it can be done using the tables. And why? Because it's cantilever beam. It has a uniformly distributed load over a portion of it and then a point load. Well, what do we need to do there? We need to, again, create two problems. The first one, we're going to just use the uniformly distributed load, and again, we know what that deflection is going to look like. It's going to look like that, and it's going to be a straight line if we analyze that problem. This problem is not in the table, but this problem is in the table. So what we're going to do is we're going to find the deflection at the end of this beam, and then we're going to extend it outward, and we're going to get the total deflection at the end. So we have, if I look at this, I don't have a P, but I do have a W naught. There's no A, there's no B. The length is 4 meters. I simply plug that into line 2 of the table. We get the delta max, plugging all those values in. I get that value for my delta max, but then I also get the slope at the end, plugging in those values also, and the slope is 0.0213. I then use my triangles here, one with the slope, the other showing the 5 meters, and we use that little triangle to get that delta C is 5 times the slope, and so we get the 0.01065 for that portion, and this portion we've already computed to be 0.0064. We add those two together, and we get that value for the delta C caused caused by the uniformly distributed load. Then we're going to do the point load separately. So I do the point load one, and now we can use line 1 in our table. We use these values. P is 20 kilonewtons, A is 7, B is 2. Our point of interest is at 9. Total length is at 9. We simply plug in those values into the equation for line 2, and I get 0.1633 meters. I then add the 0.1633 that we just calculated to the previous value. We get 0.1803 meters. So you can see that these tables, if you're clever, can be used in a number of different ways to solve problems that are not as simple as shown on the tables. Okay, I'm going to skip that and that. All right, I want to cover one more topic, and we're going to start using Poisson's ratio. If you're familiar with that, I'll just refresh your memory. What is Poisson's ratio? It's the symbol nu is the negative transverse strain divided by the axial strain. What do I mean by that? If I take, and for instance, if I take this green cube, whatever you want to call it, and I apply a tensile force at the end P, then what do I get? I get it changes from the green cube to the red cube. In other words, it gets longer in the x direction and it gets shorter in the y and z directions. And that's because of the Poisson's ratio effect. And I look at the different strains. I look at the strain, the denominator is the strain in the x direction, and the numerator is the strain in the y direction or in the z direction. You've all seen this before, so I'm not going to go through it in detail. So that, remember, if everything's linear elastic, we have epsilon x is sigma x over the Young's modulus. Epsilon y and epsilon z are negative Poisson's ratio times sigma x over E. So I get, if I know the Young's modulus and I know the Poisson's ratio, then with the applied stress caused by that force, we can get these strains in all three directions. And of course, like I say, we're assuming linear elastic behavior, where the stress and strain are related through the Young's modulus. Okay, so let's do a little example how to use this. So suppose we have a rod here and we're applying 12 kilonewtons. This is the length. We have a outer radius. It's solid, so the inner radius is 0. And so the given information is that my change in length is 0.003 meters, and my change in diameter is 2.4 times 10 to the negative 6 meters. So that's the observed behavior of this rod in the test. And we're going to say find the Young's modulus and the Poisson's ratio. Okay, what's the solution is what? Well, first we figure out the area and get the stresses. So we get the stress. So pi r squared gives me the area. My stress is force over area. So there's my stress, sigma x in the x direction. My strain is delta L over L in the x direction. And in the y direction, what is my strain? Well, it's it's what? The change in diameter. The change in diameter over the diameter. Diameter obviously is 2 times the radius. And we get that the strain in the strain in the y direction and strain in the z direction, they're going to be the same. So we get the strain is negative 0.00015. And so our Young's modulus is sigma over epsilon. And we plug in that number and we get the Young's modulus is 99.5 gigapascals. And then our Poisson's ratio is what? Is the negative epsilon y over epsilon x. We plug in our values of epsilon y and epsilon, excuse me, epsilon x, and we get our Poisson's ratio is 0.25. So just to look at this in different directions. In other words, if I have my blue square and I apply a force in that direction, I end up with the brown rectangle. If I'm applying the force vertically on my blue square, I get the pink rectangle. And then if I apply in both directions, then what our goal is to compute, what is the green shape here, the end result. And that's our goal, is to compute the situation when I have forces in multiple directions. It's pretty straightforward. We just add the effects of all these. In 3 dimensions, it looks like this. We have stresses in all 3 dimensions, sigma x, sigma y, and sigma z. And what guides us to compute this, we just add the effects in the different directions. It's called Generalized Hooke's Law. And, if I take the effects I have for an epsilon, I have my sigma over E effect, but then I also have my Poisson's ratio effect in the other 2 directions. So that my epsilon is the sum of all 3 of those. That's the basic form. So in other words, we have that our epsilon in the x direction, well, it's going to be affected by the stress in the x direction, but it's also going to be affected by the stress in the y directions and z directions through Poisson's ratio. So we end up with, we have to add all 3 of those effects. In other words, my sigma y causes an x strain. My sigma z also causes an x strain because of the Poisson ratio effect. So I can do that for all different directions of strain. This is just a reminder of what strain is. Remember, normal strain is delta over L, and shear strain, gamma, is also delta over L, but it's the delta and the L are measured differently for the shear strain. Here's my delta for shear strain. Here's my L for shear strain. So here's a little example so that we have stresses in kilopascals here. I've got my coordinate system, x, y, and z, like that. And then these are the applied stresses. We have 100, 40, and 30 in the various directions. And we have a 2 meter cube to begin with. 2 meters by 2 meters by 2 meters. We have a Young's modulus of 20,000 kilopascals, the Poisson's ratio 0.25. And what we want to find is the new lengths in all those directions. We're going to use our Generalized Hooke's Law to determine the new shape, and it's a matter of just plugging these values in. So epsilon x is going to be, well, I have the 1 over 20,000, that begins everything. So for our Young's modulus, and then I have what? Then I have my sigma x, my mu sigma y, and my mu sigma z. And I'm using that compression is negative, tension is positive. And it's just, we just plug into this expression, and we get that epsilon x is that much. We do the same thing for the others. You just have to pay attention to your axes and get your sigma x, sigma y's, and sigma z's correct. So I'm just plugging in for epsilon y, I plug into this expression. For epsilon z, I plug into this expression. Pay attention to compression versus tension, and we get that, we get an epsilon y of this much, we get an epsilon z of that much. And so we know that our change in length is going to be the strain times the original length. So there's my strain. My original length is 2. And since that is positive, we're going to be adding it. So for this one, we take the strain times the original length. It's positive, so we add it. For the last one, this is negative, so we subtract it. And we end up with our new lengths. That is how you apply the generalized Hooke's law. Okay.